Thank you for the introduction, Margaret. And I would like to thank the organizers for, well, giving me the opportunity to give this talk. So this is a joint work with Emma Lundstrom, a PhD student from Aalto University. And what is the outline of the talk today? So I'm going to first introduce what convex polytopes are. Then I'm going to talk a little bit about Earhart theory, poset theory. I'm going to introduce order polytopes and show, well, how Earhart theory and poset theory can be combined together. I'm going to focus on order polytopes of Crown posets, and I'm going to finish with some open questions and further directions. Okay, so convex polytopes are basically just a convex polytope is a convex hull of a finite collection of points in R to the D. And we have this equivalent definition that, well, we can think about a bounded intersection of a finite collection of half spaces. And we say that this polytope is a lattice polytope if all the coordinates of each one of its vertices are integer numbers. So a simple example, the unit d-dimensional cube is a convex hull of all the points in R to the G, such that each one of the coordinates is 0 or 1. Okay, now we can move quickly to Earhart theory. And to start talking about the art theory, I need to define what is the dilating by polytope. And this is exactly what you may thinking what it should be. So dilating a polytope by t, it's just multiplying each coordinate of each one of these each points by t. So with this idea, we have the lattice point enumerator, which is a function that for each dilation of my polytope counts the number of lattice points in my in the dilation, TP. So the Earhart theorem says that this is not just a function, it's a polynomial, and the degree of the polynomial is the dimension of my lattice polytope. Again, continue with our run example with cubes. The Earhart polynomial of a cube, a d-dimensional cube, is t plus 1 to the unit d-dimensional cube. Okay. We can also, well, change the basis of the Earhart polynomial, and then the coefficients of this change of basis, they are the coefficients of a vector that we call the H star vector of my polytope. And what is cool about the H star vector is that, well, Stanley showed 55 years ago, 45 years ago, that the coefficients of the H star vector, they are always non-negative and they are integer numbers. So previously the Earhart polynomial, we cannot say we know that some of the coefficients are non-negative, but we cannot say that's the rule for all the polytopes. Okay, this is what I wanted to talk about Earhart theory. Now a little bit of poset theory. So all the posets that I'm going to work with, they are going to be finite posets. And we have two, well, this is a spoiler, but we have two polynomials that are associated to finite posets. The first one is the order polynomial. So in order preserving map, is just a function that, that goes from the poset to the set of real numbers, such that if I is smaller or equal than j, in my poset, this implies that f of I is smaller or equal than f of j as real numbers. The order polynomial, well, it counts so for each n, for each number n, it counts the number of order preserving maps from P to this set N. That means that is the set of integer numbers from 1 to N. Okay. So for example, the anti-chains. So an anti-chain is a poset that the set of ordered relations is empty, and the order polynomial of the anti-chain is, we can easily see that this is t to the d. We also have this order polynomial, which we call the p-Eulerian polynomials. To define the p-Eulerian polynomials, we need to talk a little bit about the Jordan-Holder set, which is the set of linear extensions of a poset. And the p-Eulerian polynomial is this polynomial that, well, keeps track of the distance of my permutations that are in the linear extension, in the set of linear extensions of my poset P. So, for example, if we have, again, anti-chains, so the set of linear extensions is going to be SD, where D is the number of elements, and this polynomial is known as the Eulerian polynomial on D. An interesting fact about this is that this polynomial is real-rooted, and I'm going to talk a little bit about real-rootedness in the end of this talk. Okay, now I can introduce order polytopes. So this is a class of convex lattice polytopes that is defined in the way that you can see in your screen, that, well, keeps track of the order relations of my poset, in the sense that xi is smaller or equal than xj for every I that is smaller or equal than j in my poset. So, for example, the order polytope of an anti-chain on the elements is going to be the unit d-dimensional cube. So it was not just a coincidence that I chose these two run examples. It was shown by Stanley in 1986 that the Ehrhart polynomial of the order polytope of a poset is, well, the order polynomial applied as t plus 1. And if my poset P is naturally labeled, naturally labeled means, again, that if I is smaller than j in the poset, then I is smaller than j as integer numbers. So if P is naturally labeled, the star polynomial of the order polytope of P is going to be the p-Eulerian polynomial of my poset P. Okay, this is pretty much the background that we need. Now I'm going to talk about crown posets. To talk about these posets, I need to talk about zigzag posets, and have two examples of zigzags here on the slide. One with 5 elements and the other one with 6 elements. I'm going to label them like this, and the crown poset is basically, well, I'm just take a zigzag on 2 n elements, and I add this extra order relation between the first one and the last one. So what is the motivation for working with crown posets? The idea was the following. So if I add a top element and then a bottom element, so this poset now is the face lattice of a polygon. So what I want to compute is computing order polynomials, well, order polytopes of face lattices of polytopes. So the first non-trivial case would be, well, polygons. Okay. So Now I can talk about the results that we have, some of the results that we have. About the Ehrhart polynomial of the order polytope of a crown pole set, I told you before that not all polytopes have non-negative coefficients. The Ehrhart polynomial, not all of them, have only non-negative coefficients. The zigzags and the crown pole sets, they are a special class of pole sets that they have order polynomials, which is a little bit more stronger. So they have order polynomials that have non-negative coefficients. And for zigzags, that this was proved this year by Ferroni, Morales, and Panova. For crown pole sets, they also proved this, but me and Lundström, we proved this with a different approach, using the recursion that you see on the slide. And this recursion allowed us to prove the result in a more easily way. Okay, so this is one of the results that we have. The other result that I'm going to show you is like another combinatorial interpretation for the coefficients of the H-star polynomial of the order polytope of a crown pole set. So to do that, I need to talk about cyclically alternating permutations, and they were mentioned briefly yesterday by Stanley, which are these permutations. So they sort of capture, sorry, so they capture the order relations in my crown pole set. I'm gonna define this new statistic, this C-swap statistic, that is basically I look at the cyclically alternating permutation, compute its inverse, and I'm gonna look at this thing which is not really a descent, but in a recent paper by Kyle Peterson and Zwang, they call this kind of statistic like a big descent. Okay, using this statistic, what can we do? We can prove that the H-star polynomial of the order polytope of a crown pole set is given by this new statistic, this C-swap statistic, where the sum is over the set of cyclically alternating permutations. And the cool thing is that this polynomial is symmetric and unimodal. And in the next slide, I have an example where I compute the H-star polynomial. So on the right, we have the classical approach that was studied by Stanley years ago. And to the left, I have this new approach that me and Lundström are presenting to you. Okay, so there's a cool result. What else do we have in your paper, and what are the questions left? We were able to compute explicitly the F vector of order polytopes of crown pole sets, and using a computer, we verified that, for at most, n equals 200, we were able to check that this F vector is log concave. The formula is not so friendly, so we couldn't prove this. What we also wanted to show and couldn't find was a recursion for the C-swap statistic. I think that this would help in the proof of the real rootedness of the H-star polynomial of order polytopes of crown pole sets. And finally, we would like to study, face lattice of other polytopes, like pyramids over polygons, prisms over polygons. They would be natural extensions. This is pretty much what I have to say, and thank you for your attention.